So shown on this video is the envelope of the angular bisector of a point P as the vertex of this blue angle that is basically running through the boundary of an ellipse. And the angle is formed by specifying two arbitrary points in the interior of the ellipse, like so. Okay, so I specify two arbitrary points and I obtain an envelope of the bisector of Q1, P, Q2. And it looks like it's this four cusp object here, right? We saw, a similar picture in the previous video. All right. Now, of course, as I move Q around, I get Q1 around or Q2 around. These 2 points are free. I get different envelopes. One thing that I was not aware of in the previous video is that if my ellipse has a very, let's say, eccentric or elongated kind of appearance, this envelope can start to exhibit additional self-intersections, as you see here. And this is going to complicate the geometry that we're interested in somewhat, right? So now you have a curve that has a total of the 4 original cusps and 4 additional ones, so 8 cusps and 2 self-intersections. So it becomes more apparent when you get this sort of this position here of my Qs, perhaps near the minor axis and pretty close to the border. As these guys move outwards like that, you can see that one of the tangles here has been undone, whereas I still have another tangle, so for a total now of the 4 outer ones and these 6 total cusps. As I move Q outwards, I can detangle those 2 additional cusps, making this envelope become regular. But let's go back to our original setup, where I had kind of a more well-behaved outer ellipse. Right now, actually, A over B is 1.5, so this is the major axis is 3 halves that of the minor axis. And we get this phenomenon that we discussed before. Now, what do I want to show in this video additionally? I want to actually put, as before, I'm going to put Q1 on one of the foci, and what I'm superposing here now are the isocurves, or Q2, right? Isocurves of area of this envelope. So, for example, this was pre-computed by Mathematica. You can see that this isocurve here is giving me about 21% of the area of the ellipse. So these numbers here represent fractions of the area of the ellipse, right? So I can see here that these curves, they resemble circular arcs, but I think they're unlikely to be true circular arcs because there's going to be a foliation of these iso area curves, and they cannot self-intersect. So they're all going to be going through an area that is near the left side of this picture, which means that these guys, because if they were circles, they would not all be centered at the same place. So it means that they're going to go through some weird distortion near the border, and I don't expect for them to be through circles, through circular arcs. Okay, but nonetheless, this is an interesting display of what's going on in terms of Q2 iso curves of area of the envelope, right? So one way of checking if this is correct, let's take this iso curve that we talked about before, 21.6% of the area of the ellipse. I'm actually tracking this ratio up here, and it's actually showing 21.1 because this has been placed there manually, but you can see that if I move Q2 over this curve, that number tends to stay constant. Let's pick another curve here, like this one, 4.2%. You can see that I'm at 4.3% up there. So if I'm moving along this iso curve of area, I'm staying constant in the area there. So I have a couple other visualizations here. When they're both on the foci, as we mentioned before, we get a familiar curve known as the ellipse evolute or evolute, also known as the asteroid curve. Now what I'm showing here is actually one branch of those isocurves that we saw before, and that is the branch that includes this particular configuration, the evolutor of the or the asteroid, but it shows me the locus of Q2. Oh, okay, so this is not going to work. So it's showing the locus of Q2, and let's try to imagine this, for which, okay, these distorted guys would have the same area as the evolute. So the locus of Q2 for which the distorted asteroids have the same area as the evolute asteroid looks like the circular arc here. Now, then again, I think the circular arc is going to join with, become very close to the boundary of the ellipse, and it's going to circle very close to the boundary and then come back. So suggesting that it cannot be a true, this is going to be more like an oval, but this area of the oval is very circular. Okay, now another phenomenon is when I place Q1 at the center of the system, and I'm looking at the isocurves of area for Q2. Again, let's see if this is correct. Let's take this isocurve here. This one over here, 0.42. So you can see here that by tracking that number up there, you can see that if Q2 stays here while Q1 is on the center of the system, I get kind of a conservation of area. Now, for me to actually make Q2 walk exactly over this curve that was computed by Mathematica, I'm going to have to extract this particular level, okay, contour, which I haven't done. Let's go to the center here. Now I got 0.001, so this is 0.1%. You can see that this is pretty small compared to the area of the ellipse. So I'm staying within that range, and so forth and so on. A final experiment that I have here is when my 2 points, Q1 and Q2, so Q2 is free, but Q1 is a reflection of Q2 with respect to the center, right, of the system. So I can see here that my isocurves are also somewhat round or elliptic, but I've checked manually, these things are not ellipses. They're higher order curves. And there's a foliation, right? In all cases, there's a foliation of these higher degree curves. Let's check if a particular number is correct. So I got 0.27. I believe it's this contour here. So you see here that I'm getting 0.27. If Q2 walks on this contour, I stay within that ratio of areas. So this is the area of the envelope divided by the area of the ellipse. Well, let's see if I can force with this configuration that self-intersection phenomenon, and that was happening. Yeah, you can see that it's starting to break there. It's almost like a kink that prefigures the cusp. Perhaps the cusp is already there. When the curve turns from a regular curve, for example, in this situation, to something that looks like it has a kink, you can see that there's a formation of an additional cusp there. So two cusps actually. They're born twain, right? So there's two twain cusps here and two twain there. Then you can make one of these twain pairs disappear while maintaining the other. For example, maybe in this particular scenario it's not possible, but if I make them be free and I go like this, yeah, so you can see here that a pair of cusps is being born here while this area here still remains somewhat well behaved. Okay, now if I start moving Q1 towards the boundary, and near the boundary, we're going to go through a singularity, right? Because when Q1 crosses over to the other side, you get these continuities. But in any case, I think one thing that we wanted to show here, yeah, so if I decrease, for example, the minor axis, you're going to get this, these additional phenomena here, as we saw in the beginning of the video, in a more pronounced way. You can see here that there's several self-intersections. So this is going to be a rather difficult thing to analyze because we're talking about total of 4 plus 4, 8 cusps, and now we have 1, 2, 3, 4, 5, 6 self-intersections. So the geometry of these guys is not as well behaved as it looked originally, and it did look well behaved because when my ellipse is not as eccentric, the curve tends to look more well behaved. But if you investigate this thing further, you can see here that even in this well behaved ellipse, I'm already causing additional cusps to be materialized here on the left. So in any case, gives you an idea of this exploration of the envelope of bisectors to a point P running across the boundary of an ellipse, and two interior points to the ellipse in the cases where these interior points are in various positions, including one of them being in one focus, the other one being free, both being in the foci, and you get the ellipse evolute or asteroid, one of them being in the center, then you get this kind of situation here. Can I cause that self-intersection to happen if one of them is in the center? Perhaps there's an interesting affirmation here that you can't, but this would have to be further investigated. You can see here that you're already getting a kind of a fracture here, so there could be something at play here. If I, for example, make the ellipse become more yeah, so even in this case, when one of the points is in the middle, you can see that there is a fracture and additional self-intersection happening here. You can see that pretty clearly, right? So if I further decrease the minor axis of the ellipse, you accentuate this problem, further decrease it, even worse, and so forth and so on. So these things got worsened, right, by more and more elongated ellipses, which tend to produce these phenomena. Whereas if I now expand B, the minor axis, you can see that you can erase the phenomenon, and you turn this into a four-cusp curve. Okay, and so we had the case where one of the points is at the center of the ellipse, and the final case where there are reflections of each other, where we got the same problem here. You can see here there's a beginning of a kink happening here and there, and I will guess that if I make this ellipse more elongated, yes, like so, yeah, even in the reflected case, we can get one or two self-intersections, or even worse things if they're both near the minor axis. So then you get this even more complicated geometry. Okay, so that's all I have for now. See you on the next video.